In this video, I'll explain different tests for convergence of series of positive terms. I already uploaded a video on infinite series part 1 where I had explained about partial sums and behavior of infinite series using the nth partial sum. The method works when the nth partial sum is easier to simplify. Therefore, we need some other test to check the convergence or behavior of a series. So these are different tests which we can carry out to check the convergence of the positive term series. See comparison test, P series test, D'Alembert's ratio test, Raabe's test, Cauchy's nth root test, Cauchy's integral test, Leibniz test. This is for an alternating series, and Dirichlet test and Abel's test. These are few tests which we can use to check the convergence of series of positive terms. Let us see these tests one by one. The most basic of all these tests is the P series test. It states that the series summation 1 by n to the power p converges if p is greater than 1 and diverges if p is less than or equal to 1. So this series 1 by n to the power p, n is from 1 to infinity, which is 1 by 1 power p plus 1 by 2 power p plus 1 by 3 power p plus so on up to 1 by n power p plus so on. This series is called as the P series, or which is also called as harmonic series. Now take some examples. Summation of 1 by n. Here p value is 1 because power of n is 1. So p is greater than 1 means convergent. P is less than or equal to 1 means it is divergent. So in this case, this series diverges. Summation of 1 by n square. Here p is 2 which is greater than 1. Therefore, the series is convergent. 1 by root n, summation of 1 by root n, here is 1 by 2, which is 0.5 less than 1. Therefore, the series is divergent. Summation of 1 by n to the power 3 by 2. This series is convergent because 3 by 2 is 1.5, which is greater than 1. Hence, the series is convergent. So, this series, when you expand, you will get 1 plus 1 by 2 plus 1 by 3 plus so on up to 1 by n plus so on. So, that series is always divergent. Now about the geometric series. The series of the form summation n equals 0 to infinity x power n, that is 1 plus x square plus so on up to x power n plus so on up to infinite terms, then this kind of series is called as geometric series. So whenever a series is given, to check the behavior of the series, first you have to always check is it a geometric series, because if it's a geometric series then you can easily conclude the behavior of the series based on these conditions. The first condition is that this series converges if the value of x is greater than minus 1 less than 1. That is, mod x, if it is less than 1, then the series converges, and it converges to the value 1 by 1 minus x. See, for example, 1 by 3 to the power n equal to 0 to infinity, or 1 by 2 to the power n equal to 0 to infinity. So these two are geometric series. Therefore, you can check the behavior of these two series using this condition. See the value of x. Here x is half, which is less than 1. Here x is 1 by 3, that is also less than 1. Therefore, in both the cases, these two series converges, and if you want to get the point of convergence, then you will have to apply it in this formula 1 by 1 minus x. So this second series converges to 1 by 1 minus 1 by 2, that is nothing but 2. This series converges to 2, and this series converges to 3 by 2. You can apply it in this formula. Similarly, minus 1 by 6 to the power n equal to 0 to infinity. This series also converges because here x value is minus 1 by 6, which is greater than minus 1. The series diverges if x is greater than or equal to 1. 1 to the power any value is 1. 1 plus 1 plus 1 plus, so infinite terms. Therefore, the series diverges when x equal to 1. X greater than 1. See here, take this example, 3 by 2 to the power n. The value of x is 1.5, which is greater than 1. Therefore, directly you can conclude this series diverges. oscillates finitely if x equal to minus 1. Between minus 1 and 1, this series oscillates. Therefore, it oscillates finitely if x equal to minus 1, oscillates infinitely if x is less than minus 1. See this example. Take any value lesser than minus 1, like minus 2, minus 3, any value, minus 2 to the power n, then you can directly conclude this series oscillates infinitely. Therefore, the convergence depends on the value of x. If mod x is less than 1, then only the series, geometric series, converges. So, in general, if you write the geometric series, then it will be summation ar to the power n equal to 0 to infinity, a plus ar square plus so on. So, now in this case, there the first term was 1, but in this case, the first term is a. It converges if mod of r is less than 1, means r is greater than minus 1 and less than 1, and it converges to the value a divided by 1 minus r. And this geometric series diverges if mod r is greater than 1, and if mod r equal to 1, that is r equal to 1 and r equal to minus 1, r equal to 1 the series diverges, r equal to minus 1 the series oscillates. See, for example, this series 3 into 1 by 2 to the power n. Here a value is 3, r value is 1 by 2. So r is less than 1, therefore the series converges and it converges to a by 1 minus r, that is the value is 6. So in this case, r value you have to check, a value is 3 now, r value is 2, r is greater than 1, therefore the series diverges. Therefore, P series test and the geometric series are the basic series test to be conducted first. So, if you can't say the behavior of the series using those, then you have to go with some other test, that is comparison tests you have to check. See, the first comparison test says that you need two positive term series. I have taken here summation an and summation bn. These are the series of positive terms. Then for any k greater than 0, there exists m belongs to n such that an is less than or equal to k into bn. The terms of the second sequence are bigger than the terms of the first sequence. In that case, if the second series, this series converges, then smaller series must converge. And the second case is that if the smaller series diverges, then the bigger series must diverge. Bigger series in the sense the terms are bigger than the terms of the first series. So this test is called as first comparison test. You are comparing two series to check the behavior of those series. For example, test the convergence of this series. This is the given series. So we should know the fact that log of n is less than n for all n greater than 1. This condition we should know. Log n is less than n. Therefore, 1 by log n is greater than 1 by n. I have taken the reciprocal because the terms of the given series are the reciprocals of a log. So 1 by log n is greater than 1 by n for all n greater than or equal to 2. So when you take summation on both sides from n equal to 2, because the first term starts with 2, then we will get 1 by n, this series n equal to 2 to infinity is lesser than summation 1 by log n equal to 2 to infinity. Now you can apply this comparison test. So we know that 1 by n, it's using P series test, value of P equal to 1 here. P series test 1 by n, sigma 1 by n diverges. Whenever the smaller series diverges, then the bigger series must diverge. Hence, 1 by log n equal to 2 to infinity also diverges. This is called as first comparison test. Now, second comparison test. Two positive term series are an and bn such that an plus 1 by an is less than or equal to bn plus 1 by bn for all n greater than or equal to m. Then sigma bn converges implies sigma an also convergent. So same as before, but there you had in terms of multiples, here it is in terms of ratio. Whenever the smaller series diverges, the bigger series must diverge. Whenever the bigger series converges, the smaller series must converge. So summation of an divergent means bn also divergent. Sigma bn converges means sigma an also convergent. This is called as second comparison test. Next is limit form of comparison test. So this is important among all the comparison tests. Here I'll consider two series an and bn, series of positive terms, such that limit of an by bn as n tends to infinity equal to some value which is finite and non-zero. Then these two series converge or diverge together, or else you can say it in other words, these two series both behave alike. They behave in the same way. If one converges, the other also should converge, and if one diverges, then the other series also have to diverge. So that is what the meaning of limit form of comparison test. So to apply the limit form, you always first find out an by bn ratio, then apply the limit n tends to infinity and check what value you are getting. If it is finite and non-zero, then you can go with this conclusion. See, let us take one example. Test the convergence of this series. This is the given series. For the comparison test, we need minimum two series here. We need two series. One series is given. Let us see how to get the another series. So first write the nth term of this series, 1 2 3 4 and so on. So nth term of the numerator here, it is n divided by the denominator 1 2, second term 3 4, third term 5 6. So take the first term 1 3 5 7, that is odd. So it is represented as 2n minus 1, and 2, 4, 6, 8 and so on even. So it is 2n. So this is how I got the nth term of the given series. Next, you have to form the series. Summation of en is summation n by 2n minus 1 into 2n n equal to 1 to infinity. Now I have to form another series bn such that bn equal to, here take the value in the numerator n divided by, count how many n in the denominator, n into n, that is n square. That is how to form the another series. So n by n square, so 1 n cancels, you are remained with n in the denominator, therefore summation 1 by n, so that when you divide an by this bn, there is a chance of n getting cancelled here. Therefore, that is how I form the series Bn. Limit n tends to infinity. Therefore, now Bn is 1 by n, An is this value. Substitute here n by 2n minus 1 into 2n. 1n cancels here, 1n cancels, and this n goes to the numerator. That also cancels with this n by taking n common. Therefore, now when you apply the limit, why I am cancelling n, because that was the factor which was making infinity. By infinity, when you apply the limit, you will get, see, this all get cancelled. When you apply the limit, you will get 1 by 2 into 2, 1 by 4, which is finite as well as non-zero. Therefore, both these series behave same. Look at this series Bn, that is summation 1 by n. Using P series test, we know that this 1 by n diverges because P value is 1. It is divergent for P less than or equal to 1. In this case, P equal to 1. Therefore, Bn diverges whenever this summation bn diverges. Therefore, summation an also should behave in the same way. Summation an also diverges. Therefore, the given series divergent. Most of the cases, bn is usually a p series only. One more test is D'Alembert's ratio test. See here, consider a positive term series which is given as sigma an, such that limit of an plus 1 by an as n tends to infinity equal to some value l. Then this series converges if l is less than 1, diverges if l is greater than 1, and test fails if l equal to 1. Then you have to go for some other test. Therefore, whenever you are applying D'Alembert's ratio test, always you have to find this ratio first, then apply the limit. See, for example, here this is the given series. An is directly given. An equal to n plus 1 factorial divided by 3 to the power n. Therefore, let us find out an plus 1. Replace n by n plus 1. So, n plus 2 factorial divided by 3 to the power n plus 1. Now let us find out the ratio an plus 1 by an, which is equal to n plus 2 factorial divided by 3 to the power n plus 1 into, because divided by value taking the reciprocal when it goes to the numerator. So n here 3 to the power n divided by n plus 1 factorial, which is equal to 3 power n, 3 power n cancels, 1 3 remains in the denominator, and n plus 2 factorial can be split as n plus 2 into n plus 1 factorial. That n plus 1 factorial cancels with that of the denominator. So therefore n plus 2 remains in the numerator. Now apply the limit as n tends to infinity, 3 n plus 2 divided by 3. So when you apply the limit, this gives you value infinity. So this value is L, the value of L is greater than 1 now. Infinity means clearly larger than 1. So therefore, when L is greater than 1, the given series diverges. Therefore, series diverges. This is how we apply D'Alembert's ratio test. Next test is Raabe's test. Most of the time, when D'Alembert's test fails, in that case we go with the Raabe's test. Here, take a series of positive terms and you have to find this value. N into an by an plus 1 minus 1 is equal to L, that is limit n tends to infinity n into an by an plus 1 minus 1, if it is equal to L some value, then the series converges if L greater than 1, diverges if L less than 1, and test fails if L equal to 1. For example, consider this series. Now we shall find the nth term of this series. See, first term is 3, second is 3 into 6, third is 3 into 6 into 9. Therefore, nth term is 3 into 6 into 9, so on up to 3n divided by 7, 7 into 10, 7 into 10 into 13. So it is like this, 7, 10, 13 and so on. So it is in AP. So nth term of AP is A plus n minus 1 into D. So 7 plus n minus 1 into distance, here common difference is 3. Therefore 3n, 7 minus 3, 4. 3n plus 4. Therefore, 7 into 10 into 13, so on up to 3n plus 4. This is an. Next, I want an plus 1, which is equal to 3 into 6 into 9, so on up to 3n into, replace n by n plus 1. So, within bracket, n plus 1. So, that gives you 3n plus 3 divided by, because 3 into n plus 1, so which is 3n plus 3. 7 into 10 into so on up to 3n plus 4 into then 3 into n plus 1, that is 3n plus 3 plus 4, 3n plus 7. Now I want this an by an plus 1. So or else you can find an plus 1 by an also. We shall apply D'Alembert's test first. An, which is equal to, see, when you write this first, divided by this value, 3n plus 4, 3n, all those values will cancel. Then you are remained with only 3n plus 3 by 3n plus 7. Now, when you apply D'Alembert's test as n tends to infinity, this value gives, when you take n common, 3 plus 3 by n and 3 plus 7 by n. Anyway, this value becomes 0 as n tends to infinity. N cancels, 3 by 3 gives you 1. So, when L equal to 1, the test fails. Therefore, D'Alembert's test won't work here. I will apply limit n tends to infinity n into, here I want an by an plus 1. Just take the reciprocal of this. So 3n plus 7 by 3n plus 3 minus 1. Let us find out limiting value of this limit. N tends to infinity. N into 3n plus 7. Take LCM. Minus 3n minus 3 divided by 3n plus 3. So 3n minus 3n cancels. Limit n tends to infinity. This gives you 7 minus 3 is 4. So 4 divided by 3n plus 3. So as n tends to infinity, this value becomes 4 by infinity, which is equal to 0. Now this 0 is less than 1. Therefore, as per the condition, diverges if L is less than 1, the given series diverges. This is how we apply the Raabe's test to check the convergence of the given series. Now next test is Cauchy's nth root test. Most of the time when nth term of the given series is raised to some power of n, we usually go with the Cauchy's nth root test. So, for example, let summation an be a series of positive terms such that limit n tends to infinity an to the power 1 by n. We have to calculate this value in case of Cauchy's nth root test. If this value is less than 1, then the series converges. If greater than 1, series diverges. Then test fails if L equal to 1. Let us take one example. Here, an equal to n by n plus 1 to the power n squared. Now I have to find out limit n tends to infinity n by n plus 1 to the power n square whole power 1 by n. This gives you limit n tends to infinity n by n plus 1 to the power 1 n cancels n. So this is equal to limit n tends to infinity. What I'll do is I will write this n in the numerator as 1 by n plus 1 by n. I'll bring it to the denominator so that when it goes to the numerator, you'll get same thing back. This is equal to limit n tends to infinity 1 to the power any value it is 1 divided by, this can be simplified as 1 plus 1 by n to the power n. So when you apply the limit, this value of the limit, its standard limit, it is always equal to e. So this is equal to 1 by e. E value is 2.6 some value. So therefore 1 by that value is clearly less than 1. Hence the test says series will converge. Therefore, this is converges. Therefore, the given series converges because value of L is less than 1. This is how we apply Cauchy's nth root test.